Pluto is a distant and perplexing dwarf planet that was once a member of our solar system's family. However, recent surprising announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a staggering revelation. They suggested that this cold world is on a potential collision course with Neptune. But how could this happen, and what might be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon, or is there something more to this impending cosmic collision? Join us as we explore the potential outcomes of a Pluto-Neptune impact. Pluto, a former planet that was downgraded to a dwarf planet partly due to its unusual orbit, remains a subject of interest and study in the astronomical community. According to recent predictions by leading experts, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potentially dangerous collision between these two planets, which could pose a significant risk to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a stunning 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution yet. The intrigue doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, deviating significantly from the near-circular orbits of the major planets. What makes Pluto's orbit even more curious is its inclination, tilted at 17 degrees to the ecliptic plane. The path Pluto follows is much more extreme compared to other planets. This tilt and eccentricity add layers of complexity to its orbital design. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying what we might expect based on their positions in the solar system. This leads to the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to figure out its unusual path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its steep tilt and elongated shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of space mechanics. The three-body problem in space involves figuring out how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem reveals how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complicated way. The terms alpha libration and extension libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is a phenomenon called alpha libration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is found no less than 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from crossing. Extension libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned well above their orbital plane, providing an extra layer of safety from potential collisions. Another significant factor in this scenario is the VZK oscillation, named after three researchers, von Zeipel, Lyapunov, and Kozai, who studied how objects move in space. It's about how three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This gravitational pull affects how they move. In Pluto's case, the VZK helps us understand why its orbit around the Sun is so unusual. Despite its seemingly erratic path, this oscillation helps keep it moving smoothly for billions of years. The VZK oscillation shows that even if things in space seem chaotic and random, some patterns and rules keep everything in order. These factors help maintain Pluto's orbit, ensuring it doesn't collide with Neptune or get lost. This three-body problem is essential for understanding how these orbits change because of the way these space objects pull on one another. Studying this helps us learn more about Pluto, our solar system, and distant stars and galaxies. Numerical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is actually chaotic, with minor deviations in initial conditions leading to significant differences over millions of years. However, these special properties of Pluto's orbit have been found to maintain stability over very long timescales, effectively keeping chaos in check. Later computer models have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's path around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This connection helps keep Pluto's orbit stable. However, Neptune is not the only factor. Jupiter's gravity also plays a significant role in securing Pluto's orbit, and Saturn contributes as well. These studies show that Jupiter's gravity alone is strong enough to ensure Pluto remains on a stable path for an extended period, potentially billions of years. So, it's as if Neptune, Jupiter, and Saturn are working together to make sure Pluto continues to move safely in space without running into trouble. These phenomena are crucial in the context of the universe for maintaining order and consistency in the movement of celestial bodies. Without these elements, the solar system, as we know, it would be a place of much greater chaos and unpredictability. Bodies like Pluto could collide with others or be ejected from their stable orbits, leading to a domino effect on other celestial objects. For Pluto, especially in discussions about its potential future collision with Neptune, understanding its orbit is essential. This gives us a clearer picture of the solar system's dynamic nature. The case of Pluto shows how even the most seemingly unstable orbits can achieve a state of harmony through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of ongoing observation and analysis of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the strange nature of celestial bodies, and Pluto's orbit is a great example of this strangeness. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's path on its initial conditions, is clearly illustrated in the case of Pluto. This means that even slight changes in the dwarf planet's position or speed can drastically shift its long-term course. In the vast expanse of our solar system, Pluto holds a unique spot that challenges how we understand planetary formation and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant discoveries about its composition and behavior. One of the most fascinating aspects of Pluto is its surface, which is a complex tapestry of ice.